Yaskawa.
All right, well, good morning and welcome to another Yaskawa Motion Control technical webinar. This latest edition here is the latest installment of a series of webinars that we've been producing throughout the year. And they're designed to bring you application information, technical information, and some best practice implementation techniques for a variety of applications for the IEC controller. And today our topic will be kinematics. Kind of a fun topic, an interesting topic, I think. And my name is Doug Meyer. I'm one of the senior project engineers here at Yaskawa America, Inc. All right, well, let's get into the kinematics. And what we talk about when we mean kinematics is the ability to control other mechanisms besides just the standard traditional XY, XYZ. There's some applications that it's a benefit to not have a belt-driven or screw-driven type system and instead use something a little bit different. So one of the mechanisms we're going to focus on today is a Delta II style robot. This is a two-axis robot. It operates in a plane of motion, so it's a fairly straightforward kinematic mechanism. We see a lot of these in use in pick-and-place type applications, and a particular customer brought us a challenge here to be able to pick a product and place it on a stack and in the area of 120 cycles a minute or more. It's actually fairly slow for many applications, but we can go faster. And the idea was to move along a path to avoid abrupt corners. If you just do a straight down and up and straight over and down and up again, you get sharp corners, and that adds a lot of impact and shock into the system. But at the heart of all of these kinematic applications is that here in this mechanism we have motors located up here at the very top section. You don't want to program in theta 1 and theta 2. You want to stay in your user-defined reference system, still remain in a Cartesian coordinate system of say x, z. And so that's the idea behind these kinematics. So other advantages of this Delta II style approach is you can see higher speeds at the end effector. Even very long, say, X motion, 12 inches or so. If you look at the diagram, with the motors located up here at, say, the hips of the mechanism, it's very small angular motion is required to achieve large linear motion down at the end effector. Another benefit is that the motors are in a fixed location, so you don't have to deal with cable tracks, you don't have to worry about fatigue of the cables during constant bending and motion, things like that. And the mechanisms tend to be fairly stable. There's also quite a few different mechanical arrangements, permutations that are available. This is one version of a Delta II where you have your legs and your knees are here, and say these two legs are joined at a single spot. There's others that have a little linkage down there, so there's actually two joints. And there's even beyond that, this one here also has extra linkages that keep the end effector vertical automatically. So with some adaptation, we will be able to add to the toolbox here and be able to accommodate some of those others. So as you get different configurations, let us know about that and we can help develop it. Our goal even is something like this. Currently we're working on laser cannons. I have to admit this control of this type of mechanism is a little bit beyond the MP2000 IEC, but just wait for our new product, the 3200 IEC, coming out here sometime this year. We'll see what we can do for that. So as we approached this solution, we used our standard controllers. The MP2300 SIEC, it has up to 6 virtual axes, and we're going to make good use of those, as I'll show you. We use MotionWorks IEC Professional version 2. As many of you know, it's a IEC 61131-3 based environment. One of the main advantages and keys to solving this application is the ability to define your own data types and function blocks. And speaking of function blocks, that's led us to our application support tools. Today we are introducing our latest Kinematic Toolbox. It's version 200 written for IEC Professional version 2. And it has in there 2 kinematic control blocks built for you. We call it a Delta 2-1, or the first version of a Delta 2, and a 4-bar-1. So those are the 2 we're going to talk about today. We've also used some of our existing toolboxes in this solution. The gantry toolbox, which adds some coordinated path motion. The map toolbox, which helps us with our kinematics. We found we had to add an additional function called arctan2. Helps us avoid some of the discontinuities at the vertical asymptotes of an arctan function, say at 90 degrees. And also we use the Y-Motion firmware library. Inside of that is a block called Y-Direct Control that we almost want to call it Y-Classic Control. Some of you who are familiar with our standard MP2300 series controllers, where you program motion in ladder, and every scan by scan, you send an updated target position. That's essentially what this block does here for the IEC controller. All right, so overall, implementing this kinematic solution is a 5-step process. First of all, we define virtual axes in the user Cartesian coordinate system. Then we use the forward kinematic equations to be able to set the initial position of those. We make use of the absolute motors. Virtual axes don't have any absolute position. And even anytime you disable the axis, it's probably going to fall or move somewhere, things like that. So we have to reestablish our virtual axis position, and then we can enable everything. Once everything's enabled, then it's simply a matter of creating motion on the virtual axes in your user space, your Cartesian coordinate system. And then performing constantly inverse kinematic equations to transform that motion back to where the real axes are. So some of these in this 5-step process are done for you, and some you have to do yourself. So let's see what it really takes here to implement a solution like this, and then I'll get into some of the details. We find it's actually pretty straightforward. First of all, you add the Kinematic Toolbox into your project as a user library. It is now available on the Yaskawa website. It's a free download. It currently contains these 2 mechanisms, and we expect to add to this. So you'll find inside the toolbox we have a group of POUs. There's a handy link right here if you go to yaskawa.com/IECTB for IEC toolboxes. We'll get directly to the toolbox page, and you'll find that the Kinematic Toolbox is now available here for MotionWorks IEC Pro. It is not available for IEC Express because it makes use of our camming and gantry toolboxes, and camming is only available in Pro. We found that for cam calculation and execution, we really need the ability that Pro has to be able to set up multiple tasks. Alright, so once you've downloaded the toolbox, all you have to do is insert one function block into a POU. And this function block, this kinematic control block, enables the axes, allows you to clear alarms, allows you to set the 0 position for the mechanism, and all of the kinematics are contained inside. All you need to do is supply some of the linkage configuration and information about the mechanism. So we'll show you what's in this in a little bit. After that, the user is responsible for the second part of that. So after you run the kinematic block, motion needs to be created. And what we're going to show you as part of this webinar today is some example code. So we've created example code for you that takes you through the process. And this is on our website also as a free download. It's a public document. Here's the number here, EC.MWIEC.29. You can search for that, and you can also look it up by using keywords such as kinematics or example code. You can find it in a variety of ways. That's it. Pretty simple. So let's take you inside this function block here. So we'll show you a little bit about what's inside of it. With any kinematic type exercise, we need to start with a model. And so with our mechanism here, we build this and define it in terms of its linkages and angles. We show this inverted from the normal usage. Typically, this particular one is hung upside down so that items could be placed into the open top of a box, for instance, like say in a case packer. But we chose it for simplicity to model it this way and define our angles with our motors located at point A and point E down at the bottom. And so our motor angles are theta 1 and theta 2. We've also chosen to locate the origin of the mechanical coordinate system here, x prime, z prime, at point A. So it's at one of the motors, and it just allows things to work out a little more simply. So one of the givens that the user will need to supply is the distances of the linkage. They're going to vary with every application, but for this configuration we need to know L1, 2, 3, 4, and 5, and the distance between the two motors. So once we know that, then our method tells us we need to run some forward kinematics equations so that we're going to establish, with the goal of establishing this XZ position of the end of the linkage based on where the motors currently are, theta 1 and theta 2. And once we do that, then we have to go through a coordinate system transformation so that we take those mechanism space positions and translate them into our Cartesian space positions. And then we define the position of those axes. We use that with a regular MC set position. So here's what some of the equations look like. If you ever wondered back in high school, what geometry was good for, well, here it is right here. It's really fairly straightforward. But our goal here is to, given the angles of theta 1 and theta 2 at the motor positions, E and A, we're trying to find this point F right up here at the very top of the mechanism. And it's really just geometry. So A and E are pretty simple. D has a x prime, z prime coordinate. Really the only tricky part is before we can get to position F, we have the length L4 and L5, but we need to find this angle theta 4. And it is a little tricky. What we've chosen to do is kind of do use a methodology where we kind of draw an imaginary circle centered around B and another circle around point D, and one of the intersection points will be at point C. So we can use a geometry technique of the intersection of circles to find point C, and once we know that, then we can calculate theta 4 and then finally point F. That's done inside this forward kinematics block. The next step is to, once we have point F in mechanism space, x prime, z prime, we need to translate it to our user space of X, big X, big Z. And sometimes there's additional end effector offset that's going to be always pointed straight down. So that needs to figure into the equation also. This is a pretty simple equation. And now we have our end effector space where our tool is in XZ. So I'm going to jump over to the example program here real quick. I've called up this program in MotionWorks IEC version 2. And first I just wanted to show you on the library page where we've linked in all of our toolboxes, including the Kinematic toolbox. One of the things in here in the data types is we have some predefined data types. Right now there's 2 of them for this Delta 1 version, or Delta 2 version 1 linkage structure, and one for the other structure that we're going to show you today. And our POUs are in here. We have 2 categories for our mechanism and for our, so we already supplied the inverse kinematics and the forward kinematics blocks inside here. They're all located inside the Delta control, the main control block. So here's what it looks like in the actual application. The POU I spoke of here is this Kinematics POU, and you'll see that there's only the single function block right here on this worksheet. Inside here it does all the kinematic transformations. So right now I do have it enabled. I'm running this on our standard MP2300 SIEC demo kit. It has 2 Sigma 5s in it. And right now you see the current position of theta 1 and theta 2, and you also see where that is in our virtual space at roughly 0.8x and 2.9z. You can open it up and take a look inside here real quick here to show you what's in here. First of all, you see the axis control blocks that are in here. The axis control, there's actually 5 of them. There's 2 real axes and there are 3 virtual axes as part of this solution. You have your 2 X and Z virtuals that are in your main space. The third one serves as an additional virtual master for path generation and path execution. We also have some blocks that simply monitor the position. Here's the blocks that allow you to set the positions of your mechanism. And right now the template sets up a 0 position physically. You have to move the mechanism into some sort of physical spot. So on the real application, maybe you would use some sort of a stop, to go to some position and define it. For our demo kit, we decided we're going to move, as you look at the left motor to the 9 o'clock position, and that's going to be an angle of 0 degrees. And the right motor, you move it straight down to a 6 o'clock position, and that's going to be a position of 90 degrees. Here's the process I just spoke of, where we take in our linkage here for the forward kinematics. So we take in our motor position, we run it through the kinematic equations, we come out with a position for point F in X and Z, X prime and Z prime. We translate to our real coordinate system, and then we set the positions of the virtuals. Once the virtuals are have their position set, then they are allowed to be enabled. And from that point on, we take that virtual position and we go the other way, and we come out with a command here for theta 1 and for theta 2. And we feed that directly into a Y-direct control block, one for theta 1 and the other one for theta 2. So inside the block here, it's constantly streaming an updated position. Go back to the presentation here. The next main step for the user is to create movement on the virtual axes. And this can be done in a variety of ways. Some of it using just straight MC move absolute, if you want to move one axis only. If you want to move X and Y, or the 2 axes, in some coordinated way, we would use function blocks that are found in the gantry toolbox, XY move absolute, or a move path. All right. What we're going to show you next is from the example code, and it's a method of how to move the axes along a path. So this is where the user would set up what they need to do in their application. And in this application, we were taking product from a fixed location, coming in, and we were creating a stack of product. And so we had to pick up a piece and drop it off in one of 5 different layers. So we needed to generate a complete path for each one of those cycles. Pick up, drop off at one of those layers. So what the user does is start building segments. Now we can do this with a custom segment calculator. Ideally, you would do this customized for your application so that you can enter in only a few pieces of what is really the essential information, like where's the pickup point, where's the drop-off point, how many layers do you want, and how thick is the product, something like that. And once we know that, then all of these other points and segments can be automatically calculated by a segment calculator. So just so you know here, as we run this, a complete cycle would actually start at this point just above the product. It would move down to pick up the product, and then move up again and go to the drop-off point, drop it off, and then return back to that starting position. So if you count the segments, you have 1 down, 2 up, 3 around the corner, 4, 5 around the next corner, 6 to drop off, 7 back up, 8 around the corner, 9, and then 10. So overall, the whole cycle is a process of moving through 10 segments along the path. So a little bit about segment calculation. We can define paths with straight lines and with arcs, circular arcs. Straight lines are pretty easy. They're just defined by 2 absolute points, and you can set the resolution to 0 to help minimize some of the points that are in your cam. So a resolution of 0 would just give you the 2 endpoints. Ultimately, when you get to the end of your path, you're going to you have to tell the function block what number is the last segment. So you do have to add them up and give a total segment count. Arcs are a little more challenging, but not too bad. You define an arc by giving the starting and ending points of the arc, and also the absolute starting angle and the traversed angle. Now sometimes those angles are a little tricky. So if you don't know them, we've built an additional function called calculate angles. It's a little easier because now you can define this arc by giving it either the center point and direction, or by feeding it the radius. So it's a little more common way of putting that in. And then what it'll do is return to you those necessary calculated angles. So in this case, we define an arc with a certain radius, and starting at x1 z1 and ending at x2 z2 with a radius of r1. Okay. So as I mentioned, you can create this customized path segment calculator. We've done this for a variety of applications. The idea or the technique is to feed it the array of data points that you've created, and then you have custom equations inside there that'll create the segment structure that we then feed on to the path generator. In this case, our segment structure will be called paths. The next step in the process is to feed those segments to the path generator block. The path generator then loads a table into the controller memory, and it returns to you an ID number for that path. The final step would be to execute that path using the move path function block. So our little path here that we've created to pick up and drop off, we can run it. We can command it at whatever acceleration and velocity we want it to run at, and all I had to do was feed the ID into it. So I'm going to go to our example code again here and show you how that's done. So we had our Kinematics POU that has our kinematic function block in it. That's all that needs to happen there. Here's our path calculation. This is a little bit expanded because the application example actually, as I mentioned, contains 5 paths. So where you might see these typically in a straight line for a normal cam calculation, it's a little bit segmented here. So here's our path segment calculator. Basically inside here, you would be able to look inside. Structured text is a great environment for writing these kind of mathematical equations. But you see we're going through here, we're taking the information from our array, and we're creating the points, and then we're creating segments. So here's the segment that moves down to pick up. It's a straight line. Back up to the hover point. Here's our code here that goes through that first clockwise arc. And then we move on a diagonal. So such and so forth. So we end up creating our 10 segments. If you noticed, our little path segment counter here got to 10. So we do that for each of our paths. So what will come out of here is an array of path segments, and they're shown right here. Drop 1 path, drop 2 path, drop 3, 4, and 5. Next step is to take those into path generators. So you see I feed each one into a path generator, and then I get ID numbers back. So I'll get drop ID number 1, number 2, number 3, and that's it for the path calculation. The next step is to create movement. So I have a POU here called create movement, which I can either do some XY move absolutes just to any kind of coordinate position that I want to feed in, or I could go to, say, the first point, the pickup point, or I can move along a path. Say I want to execute path number 1. I'll just test it here. You'll see that the segment calculator went through segment 1 through 10. You may not have seen that show up on your screen, so for your benefit I took a logic analyzer trace, and what this pop-up shows here is our virtual Z position as the second line down in green. The virtual X is in our upper position. So you see that the mechanism went down in Z, picked up a part, then it moved diagonally to a drop-off point, and then it went and dropped it off straight down and back up again, and then it moved back to our hover point. The next lines down, the third and fourth line, are our axes, our real axes, theta 1 and theta 2. So just imagine trying to program in what these guys are doing directly. And that's the beauty of the kinematics function block, is you don't have to do that anymore. The last line here is just our segment counter. So we see it going from segment 1 on up to segment 10. To get a little clearer picture of what this really did, you can export this data to an Excel spreadsheet. And so I'll pop up the Excel spreadsheet here. So you can see again what our virtual X was doing, what our virtual Z was doing, and the nice thing about Excel is you can do an XY plot. So when you put them both together, we can validate that our path actually went down and up, and then over and down and up again, and it dropped off pretty much at the same spot for path 1. At the highest level, if we dropped off at layer 5, I took another trace, and now you see our drop-off point was much higher. And it actually was, I think we had set in a 1/2 inch thickness for each piece, so it's dropping off up here at 2.5. Okay, so I may have gotten a little bit ahead of myself here, but our inverse kinematics, just to review, the 3 steps are to translate the commanded position of the virtual into a commanded position of point F in our mechanism space. So here we simply go the other way. We do the inverse. Now we know our virtual is here, and now we have to translate back to the mechanism coordinate system. So we first get to point F, and then we flip it upside down through an inverse kinematic, and then we apply the inverse kinematic function block. So now we know point F, now we have to get back and figure out what theta 1 and theta 2 is. So same thing, just the other direction, a little bit different formulas. Here's where we use the arctan2 function to make sure that we don't have any divide by 0 problems. And then you feed that commanded position into the Y direct control block found as part of the Y motion firmware library. So here it is. Our resulting command that I showed you in the real code, command for theta 1 and theta 2, gets fed right in here to a direct motion. And one thing I should say here is that the Y direct control and all these kinematic function blocks operate in a certain task. It is application code. So they're going to update at whatever rate your task is set to be. There's an additional filter. I'll go back here. This whole kinematics POU is sitting in a task that's running at an 8 millisecond interrupt. And so we would like better resolution than 8 milliseconds at our actual motion. So we can filter this. If we put a filter into this filter time constant of the Y direct control block, then what it'll do is automatically average it over the Mechatrolink cycle. So if our Mechatrolink is at 2 milliseconds and our task was at 8 milliseconds, we get a large target position update every 8. It'll average it out and send it out in pieces, basically 25% of a time, down to the servo axis. And then, of course, the servo axes can further interpolate and divide that up across the servo cycle in between Mechatrolink updates. So even though this is running in application code at maybe what you might consider an average speed task at 8 or 12 milliseconds, something like that, we find that we can still achieve reasonably precise and smooth motion due to the subinterpolation that goes on with the Yaskawa system. The final step is to set limits on your range of motion for your mechanism to avoid crashes and things like that. This is a little bit of a rough sketch. The actual motion envelope, locus of points here, loci I guess, is kind of a strange shape depending on the mechanics here. But the user does need to be sure that all of the points that you're going to command fit within this physical range of motion. And in general, this type of mechanism, you should try to operate below the knees of the mechanism so that you don't squash the mechanism, and leave some margin to avoid full extension. So be careful about that. There are some particular conditions, ones that can create multiple solutions to the inverse kinematics. Like this particular mechanism, you want to avoid those points that would create sort of this locked leg condition, because you could actually technically move through to the other side and bend the knee the opposite way, which sounds awfully painful, number one. But number two, you just get the mechanism into some space where it doesn't operate very well at all. So be sure that your actual path does not approach that. So we do create an error inside this block. If we get within this, within a range of this position, it will throw an error to you. So this is one of the error conditions. Another condition you have to watch out for is physical linkage overlaps. The real links have some finite thickness and width. Mathematically, you may be able to move link 2 here through a full 360 degrees, but certainly in reality, you're not going to be able to do that. So there are conditions that you want to prevent here, like this one that's shown. And a third one that we monitor for is sort of this max compression, where you're trying to reach a position that's too high for the mechanism, and it's going to fold onto itself. So these things are handled in the givens and limits. So we put this in the initialization POU. So not only is it required for the linkage structure to define the lengths of the links in here, you also want to define your min and max ranges of some of these limits of motion. So in this case, we said if we get within 5 degrees of a leg being straight, we're going to stop at that point. If we compress, and we're compressing to within 15 degrees of being straight, then we're going to stop motion there also to prevent crashes. In addition to the code, we've also provided an example video in action on a real machine. This was actually a pick-and-place arm shown at PAC Expo 2011 out in Las Vegas on a blister pack thermoforming machine. And this easy link here, easy.com/delta2, is a link to a YouTube video. So I'll take it here. So we went into that one in a good deal of depth, and if that's generated questions for you, please be sure to type them into your chat area. The next one we're going to look at is the second one that's in our initial Kinematic Toolbox offering. It's a 4-bar planar robot, very similar to sort of a SCARA type design, which would be like a 2 linkage. Except that right now, this one just supports the 2 angles. We can come out shortly with a 3rd degree of motion that'll add a rotating axis at the end of this arm. But we had a particular application where this mechanism was appropriate. In this case, it actually uses 2 concentric direct drive motors sitting here at the hub where this green link is, right at the center. And this small linkage arm is actually controls the motion of the larger arm with the end effector on it. There's also z-axis on this system that is completely independent. So one of the key targets of this application was that we needed very repeatable motion. Plus or minus 12 micron repeatability was the goal, even through temperature ranges, and we were able to prove we could do that. And they needed faster moves, doubling the rate of some of the placement of pieces up to 4,000 substrates a day. But again, we wanted to reference the path in XY Cartesian space. So the process for this is exactly the same as the process for the other mechanism. Create the forward kinematic equation for the mechanism, create motion on virtual axes, and then perform inverse kinematics to stream real positions to the real axes. Same deal. Just a little bit different model. The 4-bar model has some particular advantages. First of all is that with both motors here at point M, you take some mass out of a motor that would otherwise typically be placed at the end of link 1 to control link 2. So a little bit less inertia results in faster motion capabilities. The additional link also helps stabilize L2, so you don't see as much servo dither out there. But the function block does assume a parallelogram structure. So while it's possible to have other mechanisms that could have a different junction point along L2, you can get different mechanical advantages, either maybe a resolution advantage or a speed advantage. Right now, this first 4-bar control system assumes that L4 equals L1 and that L3 is parallel to L2. That being the case, the kinematics are really the same as the standard device might be, where we calculate a theta 1 angle and a theta 2 angle. Uses the same type of function block. There's a 4-bar, the first version of our 4-bar control here. And I won't go into detail on all of that. It's really just the same with different formulas. But here is a sort of a diagram of the mechanism moving through its working envelope of a rectangle that happened to be about 500 millimeters wide by just under 250 millimeters tall. And you can see the offset here is about 250 millimeters away in X and 100 millimeters away in Y. So you see what all the linkages do as the end effector moves around from around the corners of the box. You'll see our main L2 arm is the blue one here. L1 is the red. And then so L1, the red one, is what's directly connected to one of the direct drive motors. The other direct drive motor is connected to the green link, the shortest one. We have example code for that as well. It's document number EC.MWIEC.32. You can download that from the website as well. And we also have a video for it. So I'll go ahead and click on that as well. It's easy.com/4bar. And it'll again take you to that Yaskawa page where we have some of our other videos. And this is a simple one. This is showing the robot in operation, really just in a desktop type setup, lab environment. But it's going through, it's accelerating at approximately 2G, moving half a meter in almost no time, accurate to plus or minus 12 microns if it were mounted to something stable, and instead of being mounted to just a table that's on wheels. The video actually kind of pulls away a little bit and just shows how the table's wiggling because of the high accelerations. It's not very simple, but you see it in action. Very compact mechanism, nice looking design. That was actually designed and built with our semiconductor group. So if, and I guess along with that I should mention that if the application is right, Yaskawa can help design some mechanics if it's called for. All right, that's as much presentation material as I have. At this point, we can address questions. Okay, I guess one of the questions we have is why are we doing this? Why would this not be a Motoman type of application? And certainly we are not out to try to take over what Motoman does. Motoman does some very specialized things, and they have for years. What the goal of this and what the goal of this presentation and the development of the Kinematic Toolbox is just to provide some accessory functions. So you may have a machine that already has, in fact, this blister pack thermoformer already had 8 or 9 axes of motion on it. And they decided to add this pick and place on the end. And they didn't want to, at that point, go buy an additional robot, a robot controller. They wanted to stick with the same controller that they already had, just add 2 more axes to the mechatronic network. And so that's really where that comes from. Some of these mechanisms are, it's a small machine. It's maybe doing something specialized, and we need some sort of mechanism to create simple motion. So we're talking probably in the area of a mechanism with 2 or 3 axes, maybe 4 at the tops. But certainly this controller is not going to do what a full-blown palletizing robot can do, or what a Delta 3 type robot can do. We really don't intend for this to get to that point at this particular time. But the goal here is to say, well, if we've got some other mechanism, first of all, if the controller is capable of doing it, let's talk about it a little bit. Let's see what we have. We're interested in expanding the kind of mechanisms and configuration of mechanisms that we have in our Kinematic Toolbox. So let's see where it goes. Let's find the application. Let's expand the range of things that we can do a little bit, and let's solve the problem for the customer and keep it into a single control. Our presentations, of course, along with the links, will be sent in a follow-up email. Yeah, there was a question, can we implement a Delta 3 robot? And at this point, I'd probably say we don't intend to do that at this time with the IEC controller. Certainly that would be intruding a little bit on what Motoman is working on right now. Sizing, question on sizing. And yes, it is based on the work envelope and the payload, or the amount of load that you can do. Right now, we've been working with very small, a blister pack is just a packet of pills, really. It's a pretty light load. Even the things that we were doing with that 4-bar mechanism are pretty small, That's not to say that it couldn't be done. So I was walking around the show in Las Vegas earlier, or at the end of last year, and particularly with things like case packers, you might be picking up, half a dozen bottles of bleach or something, so you're going to have some significant weight there. And certainly we could accommodate that kind of weight. It's just a matter of sizing. Some of the sizing is a little difficult, though, because of the mechanism. You get some advantages, that you'd have to work through. In that case, it's very nice to be able to model things in AutoCAD. You can apply weights, and it'll tell you exactly as you move it through the mechanism, either AutoCAD or SolidWorks or whatever. It can do some of that analysis for you. Find the worst case inertia of the system, find the worst case torque requirement of the system, things like that. So we should probably work with our customers to use those kind of tools. Sizing for this is going to be a little bit outside of what Sigma size or Sigma Junium size could probably do. As for further documentation, we will be working on further documentation to add the Kinematic Toolbox to our Toolbox help files. So we're working on that. It's not released yet. The example code right now is fairly simple and straightforward. I showed you how to use it. If you have more questions on that, you can certainly call in here to Yaskawa, but I think it's straightforward enough. You'll be able to understand what's happening there. But we will also work on a little bit of documentation for that to describe how to run the example code. But suffice it to say right now, it's designed to be run on the 2-axis demo kit, and it's very nice to show to customers. There was a question about use of, why did we choose the method to use direct control? Why the Y direct control function block? And And we chose to use that because it's the fastest way to do that kind of streamed motion command. The idea of the kinematics is that on the fly, every scan, we're going to calculate, we're going to find out where our virtual master is, and then we're going to command motion on the real axis every scan. It's the fastest way to do that. And if we were to send an updated position, I guess the alternative method would be to just execute another MC move absolute on that axis and have it interrupt. So there's two things with that, and first of all, it would be a function block that would be constantly interrupting, and there is some overhead associated with that. Whenever an MC move absolute interrupts another one, there is some execution time, so it would tend to slow down performance. The other key reason that we use the Y direct control is because we have the ability to add the filtering. And so by adding the task time in there, we can average it over the application scan, and so we get much finer resolution than we could if we used an MC move absolute. Yeah, and the final one was, I think, the idea that these webinars and the toolboxes that we provide are mainly to demonstrate that Yaskawa can help in particular applications, and to identify to you what the possibilities are. What's the range of applications that we can perform well in. So at one point we were trying to create complete solutions. We call them solution packages. Since the IEC controller was introduced, we decided to move away from that because it was a little difficult. Every application always had a little bit something different, or had a different sensor, or we had to incorporate HMI, things like that. And it became really a little bit unwieldy. So we took the approach instead, we're going to create functional toolboxes. We're going to create these software tools that you can use, you can drop in. It's going to make the programming task easier, it's going to make it more reusable. But just like we showed you in this example, you drop the one kinematic function block in, that part of it's done. Now you're down to creating the actual motion like you would for any other application. And that's up to the user. And we have tools for that too, with our path generator and things like that, to again make those calculations easier. But at some point the user does have to create their customized segment calculator. And we show an example of that, of how it can be done. But that's the point at which our channel would be involved to help the customer implement it, and there's going to need to be some engineering done to finish it off. So so take these, I guess, as a stimulus for ideas of where you can go for an application and say, oh, we need to do some mechanism. Yeah, we can. That's a couple axes. We can probably do that and throw that part of it in the rest of your machine control. As we move to the IEC platform being a complete machine controller. So I hope it helped. I hope it was informative to you. Go ahead and download the Kinematic Toolbox and feed us your suggestions on other mechanisms that we can add to it, and we can certainly help create and expand that toolbox. Thank you all for coming. We're going to wrap it up now, and look forward to working with you on these applications in the future. Have a great day.